inverse derivative shortcuts. Notation. Okay, the derivative notation, just a reminder. So the derivative of sine inverse, remember this is a function inverse, not a multiplicative inverse, but the notation is the same, but this is a function inverse. So you can think of it as the angle whose sine is x. Anyway, the derivative sine inverse of x is 1 over square root of 1 minus x squared. Derivative cosine inverse of x, minus 1 over square root of 1 minus x squared. Derivative tangent inverse of x, 1 over 1 plus x squared. Derivative cotangent inverse of x, minus 1 over 1 plus x squared. Derivative secant inverse of x, 1 over x times the square root of 1 minus x squared. And the derivative cosecant inverse of x, minus 1 over x times the square root of x squared. So we'll do some examples, and then we'll do a proof. So if we want the derivative sine inverse of 2x, we need to use the chain rule. So this is the outside function is sine inverse, the inside function is 2x. So so f prime of x is going to be follow this formula here, 1 over, but replace x by 2x, so it'd be 1 over square root of 1 minus the quantity 2x squared, and then we have to take times it by the derivative of the inside function, which is 2x, so the derivative of 2x with respect to x. So the derivative of 2x is just 2, so this is will be 2 over square root 1 minus 2 squared is 4, so this will be 2 over square root of 1 minus 4x squared. Okay, so let's do a proof that for this formula here, that the derivative of sine inverse is 1 over square root of 1 minus x squared. Okay, so the meaning of inverse function is that you're switching the roles of x and y, so the inputs become the outputs and vice versa. So if y is equal to sine inverse of x, that means x is equal to sine of y. And we can take the derivative of both sides of the equal sign and differentiate implicitly. So it's going to be derivative of x with respect to x is equal to the derivative of sine y with respect to x. And then we want to use the chain rule. So this is going to be the derivative of sine y with respect to y times dy dx. That's the chain rule. And the derivative of sine y with respect to y is the cosine of y. So this is equal to cosine y dy dx. And then so that means that okay, so that means that if we put these together, well, dx is equal to 1. So this is so if we solve this for dy dx, we get dy dx is equal to 1 over cosine of y. And the cosine is going to be, if you remember the identity, sine squared plus cosine squared equals 1. And if you solve for the cosine squared, you get subtract sine squared from both sides, you get cosine squared equals 1 minus sine squared, and then take the square root. Cosine is going to be plus or minus square root of 1 minus sine squared. Okay, so we can replace this as this is equal to 1 over plus or minus the square root of 1 minus the sine squared of y. Okay, but this is just equal to x squared. This meaning of inverse, if y equals sine inverse of x, that means x equals sine of y. And so that this is just x. So this is 1 over plus or minus square root of 1 minus x squared. But we still have this issue of plus or minus. Which is the slope positive or negative? So we have to figure that out. If you remember the domain restriction for the sine inverse, the domain is for the cosine of y is between y is between the angle is between pi over 2 and minus pi over 2. So that's the first and fourth quadrants. That's the domain restriction in order to get a sine inverse function. That y has to be between pi over 2 and minus pi over 2. So remember that. So here's minus pi over 2, and here's pi over 2. So that's in the first and fourth quadrants, and the cosine is the x coordinate on the unit circle, which is going to, in the first and fourth quadrants, that's going to be positive. So this cosine of y has to be positive. So we want the positive square root. So this is going to be 1 over square root 1 minus x squared. We want the positive square root there. So that's a derivation of the formula. Okay. So we want to sort of generalize this process here of finding the derivative of an inverse function. And so we had dy dx is 1 over cosine of y, and so that means that derivative with respect to x of sine inverse of x is 1 over cosine of sine inverse of x. And that's sort of a general pattern that is true for inverse functions. The derivative of the inverse function is 1 over the derivative of the original function evaluated at the inverse. Or another way of expressing it, dy dx is 1 over dx dy. So the slope of the inverse function at x is the reciprocal of the slope of the original function. So you're the inverse in the original function, you're basically switching the roles of x and y. And if you think of this in terms of the derivative in terms of a limit of the change in y over the change of x, you're just sort of switching those around. You're switching the x and y when you go from f to f inverse. So that's part of a general pattern that applies for inverse functions. That's sometimes useful to know. Okay, so let's do some more examples where we're applying these formulas here. I'll do one with the tangent. Another example. So the rule for the tangent inverse, it's the derivative of tangent inverse of x is 1 over 1 plus x squared. So here we can apply that to this function here. We have a product of 3x squared and the tangent inverse of x. So we can use the product rule and then apply the rule for the tangent inverse. So So it looks like I'm frozen here. There, now I'm not frozen. Okay, so this is going to be 3x squared, f prime of x, is 3x squared times the derivative with respect to x of tangent inverse of x, plus tangent inverse of x times the derivative with respect to x of 3x squared. So the derivative tangent inverse of x we said was 1 over 1 plus x squared. That's the formula. And then derivative of 3x squared is just 6x. So it's plus tangent inverse x times 6x. So usually the coefficient goes in front. So I think with trig functions and inverse trig functions, if you put if you have an algebraic expression, if it's multiplied by algebraic expression, I think it's a little bit clearer if you put the algebraic expression in front, so it doesn't look like we're taking the tangent inverse of this product here. 3x times 1 is 3x, so we'll have 3x over 1 plus x squared plus 6x tangent inverse x. Okay, so I'll also do a proof of the rule for tangent inverse. So it follows the same pattern as the one for the proof that we did for the sine inverse. Y equals tangent inverse of x. That means that x is equal to tangent of y. We're just switching the roles of x and y here. And if we take the derivative implicitly, dx dx is equal to a derivative with respect to x of tangent y, and then use the chain rule. This is the derivative with respect to y of tangent y plus dy dx, times dy dx. So dx dx is 1, so that means that we have 1 is equal to derivative with respect to y of tangent y, so what is a y here, times dy dx. Derivative tangent y with respect to y is the secant squared, so 1 is equal to secant squared y times dy dx. And then if we solve for dy dx, divide both sides by secant squared, we have 1 over secant squared y is equal to dy dx. Or usually we put what you're solving for on the left, so this is dy dx is equal to 1 over secant squared y. Okay, so let's go back to the Pythagorean identity. Sine squared plus cosine squared is equal to 1, and if we divide by cosine squared, divide each term by cosine squared, we'll get the tangent squared plus 1 is equal to secant squared. Sine over cosine is tangent, 1 over cosine is secant. So we can write this as 1 over 1 plus tangent squared y. But that's just equal to x, so x is equal to tangent y. So this is so we'll have dy dx is equal to 1 over 1 plus x squared. Okay, so that's the proof of that identity. So anyway, that concludes this presentation.